Okay, so is there anything else left in our numerical basket, numerical schemes basket, that will give us a stable solution and maybe also allow bigger time steps? Well, it turns out that implicit schemes can do that. There are many details that we are not addressing here. So even though it is it will be stable, it turns out, as I said before, there are things that may not be conserved. This is very important when you solve climate equations or weather equations. Vorticity, mass, the aerosols or concentrations of chemicals, temperatures, various things need to be conserved. So numerical methods also have to worry about overall conservation in addition to stability and overall errors that we already looked at. So here is a schematic representation of an explicit and two implicit numerical schemes. Explicit leapfrog scheme we talked about, where we used centered in space, this is centered in time and centered in space. So we said this created a numerical mode that was propagating backward in a negative x direction. And when we do implicit, we are going to solve for this, but we are going to say that's going to depend on the previous time step and the current time step. So you can see that it has also n plus 1 at m minus 1 and n plus 1 at m plus 1. So you are solving for mn. This is the c at m and n. It depends not only on c at m and n minus 1, but also depends on c at m minus 1, n plus 1, c at m plus 1, n plus 1. So this is what makes it implicit, because the current solution, the solution at the current time at the location we are looking for, also depends on values or solutions at the same time step at other locations in space. And this is another way where we are saying it depends on three previous space grids. So m minus 1, n minus 1, m and n minus 1, m plus 1 and n minus 1. Obviously this kind of spatial differencing gives us higher accuracy, and this is still depending on the two current time steps. This is something that guarantees. So this is called implicit leapfrog scheme because we are still depending on three time steps for the time step that we are depending on n plus 1 at m minus 1 and n plus 1 and m plus 1. So that's the leapfrog part of it. And this is the implicit trapezoidal method. These are just names that basically correspond to the shape or the way we leapfrog the values. So writing this rather complicated thing, so Cm at n plus 1 minus Cm at n divided by delta t is plus 1/2 of u Cm plus 1 n plus 1, so we have the same time step, minus Cm minus 1 n plus 1 divided by 2 delta x in space, obviously, plus Cm plus 1 n minus Cm minus 1 n divided by 2 delta x. So we are taking two gradients at neighboring backward and forward and dividing by 2. That's equal to 0, and writing again Cmn as in the form b to the n delta t e to the I km delta x. Then b delta t becomes, solving for this, becomes 1 minus I sigma divided by 1 plus I sigma, and sigma is here again u delta t over 2 delta x sine k delta x, just because we expanded the dependence on m plus 1, n plus 1 and m minus 1, n plus 1. Okay, so for any value of for sigma, we find that b to the delta t is equal to 1. Okay, so any value of sigma, we find the b to the delta t to be the magnitude to be 1. Only problem is that we are solving for m at n plus 1, but we cannot do that unless we also know m plus 1 at n plus 1 and m minus 1 at n plus 1, which means we have to write these equations for all the grid points with the initial value, and then they are all coupled, so we have to solve for the entire system together. So we can write the vector Cn as all the space points 1 to m at n, and our numerical discretization equation basically becomes something like this: an array of terms like minus u over 4 delta t over delta x minus 1 and then u delta t over 4 delta x. So you have the diagonal terms and the off diagonal terms. There are various details that go with it that we are not going to worry about here, and it's going to multiply the vector of c going from c1n to cmn, where m, capital M, is the total number of grid points in our domain that we are working over, plus the same thing multiplied by cmn minus 1 and so on. So this time it is n plus 1. Here we have n is n plus 1. So everything is coupled now when we go from n equal to 1 to n equal to capital N for all the time steps. Okay, so we basically end up with something like this: a times c at n plus b times c at n plus 1 equal to 0. Sorry, not all n, but n plus 1. So n and n plus 1 are coupled. So then cn plus 1, solving for the vector of all values in all x's at n plus 1. It's a matrix inversion, so obviously you know how to do the matrix operation. Minus b inverse of a times cn. So this is what is added as heavy computational value, but because you can imagine, the larger the domain, the larger the matrix, and we are only talking about one-dimensional system here. Obviously in reality we're going to have three-dimensional systems, and that's going to be a real big computational problem as well, and then you have to worry about the matrix properties and so on and so forth. So how do the solutions look? Look very similar to what we had before with the centered in space and centered in time. So it is capturing the peak, but you can see that when you change the time step, you change the solution in terms of where the peak is. So here, comparison of the exact solution again with the thin blue line moving to the right direction in positive x, with numerical solutions of the advection equation using implicit trapezoidal scheme that we mentioned here. So we are using this scheme. We can also do this with that, it doesn't matter. With two different time steps, delta t equal to 0.1 in the black curve and delta t equal to 0.5 in the red curve, with delta x equal to 0.2 for both and u equal to 1. The initial condition at c equal to 1 for minus 1 less than equal to x less than equal to 1 and c equal to 0 elsewhere. That's the initial pulse given. Both schemes reproduce the main maximum relatively well. Depends on your acceptance level of the numerical error, but they also generate numerical modes propagating to the left. The method with the large time step exhibits a greater lag of the main maximum. Okay, so you can see there is not much damping. In fact, there is a false peak here that gets damped and then gets lagged. Obviously this is a stable method, but which means it allows you to take bigger time steps, which saves you a lot on computational time, which of course is increased because of the matrix inversion. So you are trading here. you are finding a stable solution which allows a bigger time step, but you have to invert a matrix, and you still have the numerical solution. So essentially, discretization is going to give you numerical error in some form or the other. Stability is going to require either CFL criterion be met in the case of upstream spatial differencing, but there the peak is damped and dispersed, whereas in the implicit method the peak is better captured, but you still have the error propagating to the left. Okay, so we'll come and look at other issues as we go forward in the next podcast. Okay.